How did it on?
Yes.
Oh, we were able to record yesterday?
Yeah, the previous one worked, yeah. All right, so today I'm going to be, let me just give a brief review of everything that we've done so far. Just another review. So of course, we're interested in the differential equation. X, right? And X, as I said before, is going to be alpha Holder. Generally speaking, dx dt. Thank you. Yep. So we're assuming that X is in C alpha. In particular, most cases of X are not differentiable. So again, just, you're writing this as a integral equation. And just want to remind you of one class of processes we would care about, which would be the fractional Brownian motion. So it's a centered, continuous Gaussian process. So that the covariance where H is in 0 to 1. And of course, we had talked if H is 1/2, we recover regular Brownian motion. If H is greater than 1/2, we're able to handle this with Young theory, and then H less than 1/2, we have to do the rough paths theory. Okay, so just a couple reminders of this fact. For all alpha less than H, DH is in C alpha almost surely. So facts. H equals 1/2 is Brownian motion and is the only semi-martingale. And today I'm mostly going to want to talk about the relationship between stochastic calculus and rough integration, rough path theory. In particular, just with the Brownian motion. Okay. So yesterday we had talked about it's the Salian-Victor extension theorem, which allows for any signal X and C alpha between 1/3 and 1/2, we're able to extend it to a rough path, right? But the extension seemed a little bit odd or a little bit ad hoc, right? So today I'm going to be talking a little bit about more natural extensions, or more natural extensions of a Brownian motion to a rough path. So, particular, I'm going to talk about at first the Ito rough path and the Stratonovich rough path. Okay, so recall The Ito theory is that you define for Z progressively measurable and almost surely in L2. I'll write that soon. You write this as the probability limit. Z of TK. Times, let me just write B of TK, TK plus 1. So you define it as a Riemann sum, except you take the limit in probability, right? And then this exists if Z is progressively measurable and if the probability that it's almost, so if it's progressively measurable and almost surely L2, we can show that this limit exists in probability. Okay. So let's talk about the relationship between this Ito theory and the Ito rough path. So you can check that the pair, so it can check that the pair BST, the Ito ST, where BST Ito is this double iterated integral you can check that this is a rough path, which shouldn't be too surprising. And check that this satisfies the two conditions that the second order part is 2 alpha holder, and also it satisfies this chance relation. Okay. It's not too hard to check. Definitely on the diagonals, it's really easy to check because you have an explicit expression. Then on the off diagonals, it's not that hard as well. All right, so now there's this interesting theory of, okay, so we know when the Ito integral exists. Now let's talk about the rough integral with the Ito or with the Ito lift. Okay. And one thing is that there actually is kind of one reason why some of the Ito theory is actually a little bit nicer here is because the Ito theory in some ways can handle a larger class of integrands, right? So recall from yesterday, I'd mentioned about a controlled rough path. Let me just remind you what that is as sort of the class of integrands that we're interested in integrating. Called definition. Given X in C alpha, we say Y in C alpha is controlled by X. If there exists Y prime in C alpha, so that with RST in C2 alpha. So if we have this kind of Taylor type expansion. So one very classic example of this Taylor type expansion would be if y of t is equal to f of x of t, where f is C1, for example. Another one would be if y of t is deterministic. And y is in C2 alpha, right? Because then you could just choose y prime equals to 0, y of t minus y of s is just equal to r of st, where r of st is in C2 alpha.
This is kind of like I don't think it is properly, right? Saying that one, y is in some sigma alpha generated by x because it's a function of x. And it's just talking about some additional expectations. Interpret that as kind of a right-off derivative. That the differential in y is given by something, a density times the differential of x.
Yeah.
So kind of, absolute continuity for rough path. And then up to, yeah, something else. Yeah.
Up to some, sufficiently nice.
Whatever, over is wrong.
Yes. But one thing that I wanted to compare is, okay, so I haven't talked about this. So the proof that you can define a rough integral for these control paths is they're called the Sewing lemma. I haven't actually proved that yet. But one thing I did want to compare that I think is really important is if you look at the Ito theory, well, the rough path theory is pathwise, right? So this guy, we don't care about that at all, right? We don't care about probability at all, in terms of defining and showing the existence of a rough path, right? But this guy right here is significantly weaker than the regularity conditions we have on the controlled paths, right? So just one thing I wanted to mention is that, for example, if we have integrand here, an integrand here is z that's not C2 alpha, that's deterministic, it's not in this class, right? It's not in this class. So this is one kind of issue with the rough integration, is that it allows us to generalize the process we're integrating against. It allows us to generalize the kind of probabilistic properties we have, but it restricts the class of integrands. And that's a really important point, is that, you take whatever, z of s equals t to the 1/4 or something like that. Rough paths can't even handle that, right? You need to have nice integrands here, much nicer than the Ito theory. Okay. Yes. So you need condition on that, but here all you need is just a L2 condition. Yes. Smoothness results of semi-martingales. So as I had said, at least for a martingale, if you're differentiable, then you're constant.
Whether general
in general, I would think it would be a pretty hard to get some kind of result like that. Maybe there is, I don't know, but generally speaking, I don't see a kind of result like that. Yeah, so well, deterministic, that's bounded variation plus Brownian motion. But just for like a general martingale, I don't know if you can get anything nice in terms of the Holder regularity. Maybe you can. I'm just not aware of a result like that.
Theory allows you to do integration against the general schema.
Sure, right? So, yeah, so Ito theory lets you do, so if you were able to construct a martingale that was an alpha holder, then you would be able to use these, you would be able to use the Ito theory, right? But not the rough path, right? Yeah. Well, I mean, one thing to keep in mind is rough path also works. I've been doing everything in terms of alpha holder, but also works in terms of P variation as well. So that's another thing as well. So actually, you know what? Never mind. So now that you think about it in terms of that, right? So for a martingale, it always has a finite quadratic variation, which will tell you about the P variation. So never mind. Actually, yeah. Finite quadratic variation tells you about the P variation. Yeah. Okay. All right. So one other thing that I wanted to point out as well is rough paths tells you one thing that I think is really nice about why the quadratic variation in stochastic calculus is so important. And it comes down to, so rough path theory just tells us that this iterated integral here is the this iterated integral kind of fixes your integration theory. It's your iterated integral tells you what kind of integration theory that you have. So let me just show one small computation with the just for a Brownian motion, right?
Oh, that's not the property.
Yeah, this is just Brownian. I'm just considering the Brownian motion right here. For fractional Brownian motion, depending on how low, you might need 4 or more iterated integrals. But let's just say for Brownian motion, then you have that. Let's just take a look at this guy here, which again, if we're defining it as a limit in probability, this is equal to P limit as n goes to infinity of u. Let me just write it this way. Which we can add and subtract. Right, if we just add and subtract there. So one thing that I wanted to point out here is, of course, it's just a constant, right? But this guy right here is a that is the quadratic variation, right? So again, we know that this is 1/2 squared of t minus 1/2. Let me just use brackets to denote the quadratic variation. Which of course, just 1/2 e squared of t minus 1/2 t, right? So let me just write it this way: quadratic variation at time t. So one point I just wanted to make here is that this demonstrates in the Ito theory why the quadratic variation is so essential, right? Is because as we've shown that if you can define this iterated integral, that sort of fixes the theory, fixes the integration theory. And then here, all you have to look at is this term in the Riemann-Stieltjes sum. So once you make sense of what that term makes as n goes to infinity, as in, for example, quadratic variation, which is just defined as the limit in probability, then you fix the rest of the theory there, right? So being able to pick out the iterated integrals tells you everything you need to know about what the theory is. So in that way, you can think of rough paths as sort of a theory of integration theories. Each time you enhance it with a different rough path, that corresponds to a different theory, right? And that's that's one way of thinking about it, is these are like a set of all possible integration theories. Now you can go to ones that aren't rough paths, but all integration theories that satisfy these kind of basic properties, right?
Integration theory.
I mean, like, so if you're given a Brownian motion, you have, for example, the Ito integration theory, and you have the Stratanovich integration theory, and then you can include other integration theories as well. So it's just saying that these are all the admissible like integration theories above a Brownian motion. Ito and Stratanovich are just two admissible integration theories above Brownian motion. Absolutely. Right. And you can choose all of those, or you can just go straight to the rough path, and you can just like add and subtract these different Fs, right? And those all correspond to different integration theories, right? And in particular, that's the next thing I wanted to talk about was, okay, this is the Ito integral, the Ito rough path. Well, we can just add a 1/2 t minus s to it and recover the Stratanovich rough path, right? So this is so we have the B, let me write kind of bold B here. B Ito. This is bold B Ito rough path. And then you can consider the Stratanovich rough path. Where that's just the identity matrix. So keep in mind, all of this is d-dimensional. I'm just ignoring the tensor products just in the interest of time. So this is the Stratanovich rough path, and t minus s, the function f of t equals t. That is certainly 2 alpha holder, right? So this is a completely acceptable new rough path. So these are 2 examples of rough paths above a Brownian motion, the Ito theory and the Stratanovich theory. Okay, and if instead of t minus s, you wanted to put, I don't know, some other function there, t squared minus s squared or something like that, that would be some other integration theory as well. And you can just keep on adding whatever you want. But generally speaking, these are going to be the 2 integration theories that we like. Yeah, so at least on the diagonal, right? So the Stratanovich is a geometric lift in the sense that we can approximate it by smooth paths, and it's also geometric in the sense that the symmetric part of the second order term is just the tensor of the first order part with itself. So you can just show, let me say this is just a second ordered part, comma I is just 1/2 T, 1/2 BI of T minus BI of S squared, right? Because that's just the Stratonovich integral of a Brownian motion against itself is just going to be 1/2 of the increment squared. The off-diagonal terms is going to be a little bit harder to write, and this is generally going to be the case. The off-diagonal terms for any rough path are going to be harder to write down in an explicit way, but you can show that, can show that it's geometric. So, which we'll talk about shortly, actually. So, it'll be basically the same. So, because I mean, it'll be the same in the sense, because if you look at the definition of controlled rough path, there's nothing that has to do with the second order term, right? It just has to do with the first order term. So it doesn't increase if we're trying to deal with a rough path, right? One more thing that I wanted to mention, though, is that, all right, so there is some intersection of admissible integrands, right? So if you deal with an integrand that's progressively measurable and almost surely L2 and also controlled in the rough path sense, then so just theorem. Let, be Ito be the Ito rough path above a Brownian motion. Brownian motion. All right. Let Y be controlled by B. Okay. Let Y be controlled by B, and let Y, be progressively measurable. It's controlled by, let me just write almost surely L2. Then almost surely we have that Y of S dB Ito is equal to Y of S dB of S. So this is the Ito rough integral, and then this is just the Ito integral. So this is Ito integral. This is Ito rough path integral. Okay. So when both integrals are defined, you have that the rough integral and the Ito integral coincide. Okay. Well, controlled by, so if it's progressively measurable means it's a function of V, right? And then it's also controlled by, so we have this kind of remainder term as well, right? But the point is, when both of these exist, they're equal to each other. Okay. Now you might have the issues where one exists and the other one doesn't, but they coincide. Okay, which is kind of a good check that this rough theory is not dumb. It's like we can recover the at least when everything works out, we can recover the standard integration theories. Okay. If Y is controlled by B, in the sense that I said earlier, if we have that kind of like Taylor type expansion.
Could have one go up fine.
Yes.
The other one will.
That's right. So like, for example, the Ito integral might converge if Y isn't sufficiently Holder regular, right? And the rough integral might converge if, for example, if Y was not adapted. So if you had like, I don't know, a Y of capital T or something like that in here, the rough integral doesn't care about probability at all, right? So you can just integrate functions against B, right? But here you require progressively measurable. So you might not be defined. So here you can weaken some of the probabilistic properties. Here you can weaken some of the analytic properties. But when you have both nice enough probability, nice enough analytic, then they equal to each other. Okay. All right. So one thing that is really nice about the Stratonovich, in the sense that it's a geometric rough path, is that we have a integration theory for it, or a approximation theory for it, which is a really nice property of it. So we're not even talking about differential equations here yet, but yeah. So one further question you might have would be, well, let's say you have an Ito differential equation, then you have a rough differential equation with the Ito rough path lift. And I believe it's if you have a strong solution for the Ito equation, then it is equal almost surely to the rough, as long as both of them exist. I believe that's true. There might be some other like minor details, but yeah. Yeah, so basically when everything exists, things coincide. When they don't exist, they might exist one side or not the other. All right, so let's talk about what's called the, I'm gonna state just a couple results for random rough paths, so for example, I'm gonna state a Komarov continuity criterion for a rough path, which is, I'm not gonna prove because it's basically exactly the same proof as the standard Komarov continuity criterion. But I'll state it, and it is very useful. So Komarov continuity. Yeah. So let Q be greater than 2, be greater than 1 over Q, and assume that we have for a, so assume that we have a first order and a second order term that are Q. So this is just, just the increment of a function taking values in RD. And the LQ norm. Okay. Is that? All right. Then then for all alpha, there exists a modification of so that, let's see, yeah, modification K alpha 1 in LQ of omega, K alpha 2 in LQ over 2. And this is omega, this is a random variable, such that we have the pathwise estimates and this is really of an omega. I'll drop it here, but this K1 is a random variable. Sorry, it should be alpha. It's 2 ST K2 alpha. So 2 alpha. Yeah. And, you know, even further, if alpha is in if alpha is in 1/3 to beta minus 1 over Q, then we have that it is a rough path in the space C alpha almost surely. It's a curly C, the space of rough paths alpha. So there's a lot of bookkeeping here, but there's not really too much deep going on other than it's just a generalization of Komarov continuity criterion to the rough path. So if you have an LQ, yeah, if you have a LQ, then you if you have LQ norms in terms of the random variable, then you can get that it is almost surely a C alpha rough path. Yeah. And then you can use this to construct rough paths above, say, Brownian motion or things like that.
So X1 ST is the random difference, right? Say something that can with respect to the probability.
That's correct. That's right.
But then you put in K alpha of omega.
It's just another random variable.
Okay, but so it's not, so but now you evaluated omega, so what is it after you evaluate it?
Just a real number.
Okay, so then you should just say K1 of alpha and L2, right? You evaluated it's a number now. What is it?
Sure.
Number. Okay, so it's only very.
Yeah, so it's K1 alpha. Actually, I think that should be over. I mean, for a Brownian motion, really, you're going to apply. So you can apply, because it's Gaussian, you can apply any Q, and then you can get basically any alpha less than 1/2. Right. So you can take. Right. So for, say, the increment of a Brownian motion, you can take this to the power of 2 to the power of 2n, and then you get a Cn T minus S to the B2n, right? And then you can use this result to get alpha less than 1/2. So you can apply this for any Q if your process is Gaussian, for example. Yeah. Well, sorry, beta should be greater than, so yeah, so beta is greater than 1/Q. Hold on one second. So Q is greater than or equal to 2, beta is 1/Q. Sorry, 1 second. Yeah, eventually you're gonna want beta to go up to 1/2, but I think you have, sorry, 1 second. Let me take a look at this. Beta 1/3 is greater than. Let me get back to you on that. Yeah. But the point is, all the indices, all the variables aside, if you're able to find LQ norms, then you're able to get almost sure existence inside the rough path space. Mm-hmm.
The concept that make the folder in the
Yes.
yeah.
Uh-huh. That's right.
Randomness, they may depend on the path.
Uh-huh. Yeah. That's right. Yeah, so let me just conclude with a couple propositions and actually a theorem of mine.
And the folder norm is a nice random function.
Yes. Uh-huh. Uh-huh. That's right. That's right. Yeah, so this includes, if you just forget all the second order stuff, this includes the standard Kolmogorov continuity. Although you can't apply the standard Kolmogorov continuity to like some, just to like both components, because the Chen's relation has some cancellations. That's a really important point, is the cancellations from the Chen's relation allow you to do a little bit better. Okay. So let me just conclude. Yeah, go ahead. Oh, modification. It just means that it's a modification of a stochastic process is just one that the probability that for all time the distributions are going to be equal, right? Yeah. Okay, so let me conclude with just a couple you're asking separately for each t, so it doesn't, so it's like a for all t the distributions are equal versus yeah, versus they're equal as paths would be indistinguishable. Yeah. So let me just conclude with a couple of statements. And then I'll also include a theorem that I have that so proposition. So proposition, let Bn be piecewise linear dyadic approximations to Brownian motion B. Okay, meaning Btn is equal to Bt if and linear otherwise. Then with probability 1, Bn, Bbn converges to B strat. In say C alpha for less than 1/2. So you can take dyadic approximations. You can enhance it with the piecewise linear interpolation. And then you can just take the limit in the rough topology, and then you end up with a just Brownian motion with a Stratonovich integral. Okay. And one really important thing is the Ito integral is not geometric, so you're not able to approximate the Ito rough path by taking some kind of approximation like this. Okay. And generally speaking, so one thing is you can change the exact approximation you do, and there are times where you will get different lifts if you change the kinds of approximation. However, generally speaking, when people say geometric lift, they're going to be talking about this one. They're going to be talking about the one where you do a piecewise linearization and then take the limit there. And that's generally speaking, if someone says the geometric lift, that's what they mean is going to be something like this. So this is true for Brownian motion. Then you can also show that this exists for fractional Brownian motion and a bunch of other processes. And let me just conclude with a result of mine. So if you're in this and you have all this fancy machinery and you're wondering, like, is this really necessary? I have a result saying, at least for Gaussian processes, in some sense, no. So let me say a result that I have. So the theorem. Basically let X be, let's see, d-dimensional Gaussian process. Say the full conditions are a little bit more complicated, but say at least with this. Okay. So then it admits geometric rough path so it's 3 because we're greater than 1/4 here. Let Y be controlled by X. Then you take the just midpoint. That. And this limit equals almost surely the rough integral. So this is for any Gaussian process for including FBM for h greater than 1/4. So you take emitting geometric in this sense that you can piecewise linear approximate it. Then you just take this midpoint rule here, and then this converges almost surely to the rough integral above x, with the geometric rough path, right? So there's one result that I have. If you want to avoid all of this technical nonsense, you can just take this midpoint rule. To any Gaussian process for h greater than 1/4. Yep, and it exists almost surely. Mm-hmm. Yeah. Yep. Exactly. So I just show that the Stratonovich. So it's well known that the Stratonovich exists almost surely for Brownian motion. Here, I just generalized it to any Gaussian process, including FBM, things like that. Yeah.
Say using a rough path. So I forget how. Is it already a theorem that there is one, or you have to assume that there is?
It's a theorem that there is one. So for any Gaussian process with h greater than or with alpha greater than 1/4, you can find an approximation like this. Yeah. For alpha less than 1/4, things become a bit more complicated. But yeah. Uh-huh.
And what happened?
In terms of, so the issue is, I can even show this at one point with FBM, is that, so we have this Volterra representation of FBM where we can represent FBM as an Ito integral. And basically if you just do this representation and then try to look at the singularities that are in there, these singularities are going to be integrable if h is greater than 1/4. Now, when h is less than 1/4, some of these are not going to be integrable. I would take me a few minutes to kind of explain some of the heuristics of that. Another way of looking at it is through 2D Young integration. So one thing that's kind of funny is, so Young integrals exist if f and g, if the sum of that is greater than 1, so the whole regularities there. You can do 2D Young integrals, which sort of like allows you to cut that in half in some way. So then half of 1/2 would be 1/4. So as long as the whole irregularity is greater than 1/4, you can use this 2D Young integration methods. There's a couple of different things, but really the 1/4 is kind of a hard boundary. And you can construct a rough path lower than that. It's just not going to come from any kind of nice approximation procedure or anything like that. But you can construct a rough path below that. Uh-huh. Yeah, and you're able to have this, and also this shows somehow, like we say that you can define anything you want above a signal, right? But here it kind of shows that this geometric is somehow canonical, right? That there's sort of a natural choice, which is the geometric in this sense. There's a natural choice of rough path above a signal. It's going to be the ones where you can do an approximation procedure. So if you're not geometric, then you can't approximate, which is in particular really bad. So in terms of solving RDEs, so for example, the solution map for RDE, for a rough differential equation, from the noise to the solution is continuous. So if you can approximate the noise, then you can approximate the solution, right? But if you can't approximate the noise, then you can't approximate the solution. So, or maybe there's sometimes you can, but in general, you don't expect to be able to approximate the solution if your rough path is not geometric. Uh-huh. Uh-huh.
Construction, and I think the theorem talking about
This one right here. Mhm. Mhm. Yeah, so I in general, it's going to be quite hard to say that, right? It's going to be quite hard to say that there's a a natural approximation. So one thing is, even if you find an approximation, whether or not that approximation is natural, right, is an important question. And one thing, by the way, so I haven't shown this, but I do believe that we can show this result here for a higher ordered like quadrature rules. So rather than taking trapezoid rule, all these other quadratures, you could take Simpson's rule that have just better error properties.
In this position, if you imagine constructing the round walls instead of like this round walls, presented as a random Fourier series running through. And then you truncate the series, you get a kind of product with random coefficient with the same kind of
I think you would get something like that. You might get so you would get a geometric rough path, but like you can always add an anti-symmetric part to this, and then it would still be geometric because the symmetric part is still going to be what you want, right? So at the very least, we would say it's Stratinovich plus an anti-symmetric part. And if you know what that anti-symmetric part is, you can maybe just, try subtracting it or something like that, right?
Yeah, you don't exactly the one spot.
So the results I have here shows that it converges to a particular rough integral with a particular rough path lift. But in general, you're not at all going to have a unique rough lift for a signal. And generally speaking, because, for example, like I was saying, like the Ito theory or the Stratinovich theory are two totally acceptable rough path lifts. But they're fundamentally very different, and even beyond just having two, you have infinitely many of them, and basically all of them are sort of related by you can take just one rough path lift, and then you can take the increment of a 2 alpha holder function, and then those are going to give you all the other rough paths, all the other rough path lifts. So for Ito, it's just going to be Stratinovich minus 1/2 t minus s. But then you can just keep on adding different ones. So rather than t minus s, you could do t squared minus s squared or a bunch of other things. And these are all acceptable lifts. But yeah.